lab colloquium. Professor Madhu is with us today. So Madhu is a Gordon Mackay professor in the John A. Paulson School of Engineering and Applied Sciences at Harvard University. Madhu got his bachelor's degree from IIT Delhi in 1987 and his PhD from UC Berkeley in 1992. We all grew up watching his videos, and so it's a privilege to have this.
Okay, so thank you so much, Sujoy. Thank you all for coming. This was sort of arranged at short notice, so I appreciate all of you who are here. So this is a result of a long series of thoughts that I've had on knowledge, how we communicate, how we reason, and in general, whenever we're thinking about any object which is being communicated or reasoned about, there is a possibility of errors, and once you have possibility of errors, you have to ask the question, so is our knowledge robust? Are we learning interesting things which are actually correct? So why ask this question of, is knowledge robust? Well, every one of these processes that you use to build knowledge is actually prone to errors. So you start by collecting some data, errors can happen, you're analyzing, errors can happen, then you sort of combine results, you sort of look at papers that others have published, and then you say, okay, based on all of these results and my own findings, I conclude something else. Well, the things that you're using may be erroneous, or the things that you are deriving may be erroneous. So this just, as you go along and as society becomes more and more complex and the knowledge infrastructure gets more and more complex, what's the odds that somewhere along the path there's no error, there's an error? I mean, it seems like this should be exploding as a problem, and unless there is a way of studying this carefully and trying to understand where are the error control, error correction controls being put in and how effective they are, we are going to end up in a very precarious position. And this is something that sort of bothers me, and I'm not even thinking of malice involved over here, no malicious parties, just benign errors happening, but it's inevitable. And we have to think about, so is it a mistake of our knowledge infrastructure, the scientific method, that errors happen? And I don't think so. I think we should always try to design an infrastructure which allows for errors so that there's also chance of progress. I mean, if you spend all your time checking for errors in previous works, then you're going to spend all your time checking for errors and there's no progress. If you allow for a little bit of error, there's probably lots more possibilities for making forward steps. But now you have to worry about the fact that these few errors that have been introduced along the way sort of spread out so much that it is dominating all our eventual knowledge. So there's also got to be control. You can't just let it go wild. So this was the kind of thinking that led to this project, and some examples of mistakes that have happened in the past. So Lebesgue apparently proved in 1904 that a projection of a measurable set is measurable. I don't know what that means, but well, this is a paper which has lots of citations, and many of these citations happened in the early days when the paper was out, and they were in particular prior to 1917, which is when Sussman discovered a counterexample, and he said, okay, look, there is a projection of a measurable set which is not measurable, so the theorem is wrong. It's not just proof was wrong, theorem is wrong, no fix. So according to my collaborator Dan Michelchiner, this is actually a happy ending because the error in Lebesgue's paper and the correction led to a whole new theory of descriptive set theory, but we are more worried about this particular result in this paper, which has been quoted and has been used, and now it turns out this is wrong. So what are we going to do? And this is not the only example. In fact, math has fewer of these examples than other areas, but once you go into areas like medicine and so on, this kind of contradictions are rife. I mean, apparently in the 1960s, there was this huge collection of papers which are even funded by some interested parties, which said that, oh, sugar is completely benign and fat is the only problem. And now in this newly published article in 2016 in the Journal of the American Medical Association, I believe, they say, oh, look, this entire field of study was wrong, and now the entire output of that field and its consequences have to be dismissed or overwritten. And in the meanwhile, this research is going on, so others are probably building on this paper. If anybody built on this paper directly, probably they might have heard about it by now and retracted it. But what about the people that built on this paper indirectly, the second ones, the third tiers and the fourth tiers? They still exist and they may be still working. So this is the kind of a process that we want to study. But I mean, you all know I'm a theoretician, so are all of my collaborators. We are not going to actually look at actual data and do an actual analysis. What we are going to do here is try to think about this as a simple probabilistic model and try to understand what kinds of phenomena does this model tell us. So this is going to be a model which will talk about how knowledge accumulates, how errors can be introduced, what kind of mechanisms there may be to control these errors, and given this combination, how effective is this? Okay. So this is the kind of question: can we guarantee that the effects caused by a single error do not propagate too much? Okay. So in order to do this, we introduce this thing called the cumulative knowledge process. So the basic things that we will try to introduce are what are units of knowledge. For us, it will be some very simple graph theoretic model. Every unit of knowledge is represented as a node in a graph. Dependencies on knowledge are given by directed edges. So if this edge points, if this node has an edge going to this one, it means the new node depends for its correctness on the previous one being correct, or all the incident ones being correct. Okay. And then we will try to talk about how errors can be introduced, and then how they can be checked and removed, and then to see what kind of global effects we see as a result. Okay. And by the way, feel free to ask questions at any point. Just raise your hands or just speak up. All right. So knowledge in our case should be represented as a directed acyclic graph. I mean, we shouldn't have a chain of dependencies which are cyclical. This should also represent the notion of time. I mean, at the moment you are publishing a paper, you should sort of cite previously published ones, and so we don't want to have cycles over here. We shouldn't have cycles. And vertices represent units of knowledge, edges are dependencies. Okay, so this is the kind of thing that we want to study. The unfortunate thing here is that in order to understand what kinds of papers should a new paper cite, even coming up with a simple probabilistic model is non-trivially challenging, because you shouldn't be citing two random independent papers from the past. Okay, I mean, what are the chances that some paper that I write will cite some paper in zoology and one in medicine? I mean, it's, and maybe one math one too. So this required a more sophisticated knowledge, understanding of the structure of the knowledge, and we didn't want to get into that business at this moment. So we said, okay, let's simplify this story greatly by just saying, okay, every paper depends on only one previous paper. Okay, so knowledge now is represented by a tree. This is just for starting purposes. We can definitely extend the model to allow for a general DAG, but then you should have a good probabilistic growth model for a DAG, which we don't currently have. And then we could ask many of these questions, but at least we could get a flavor of the questions one can ask by just looking at a simple tree model. Okay, in a tree model, it makes sense that a newly published paper whose identity I don't know will cite some random previously published paper, because this is that's the notion of just new knowledge. Okay, so the knowledge model is from now on going to be a tree. And as the node is produced, each node will have a hidden state. Okay, and this is where errors are getting injected. So a node is conditionally true if nothing was wrong in its derivation. Okay, so it depended on this previous one, and it really does say that the previous result implies the new one, but it doesn't say that the previous one is right. So it's not necessarily true, it's only conditionally true. Okay, so a node that is conditionally true is actually true if every previous ancestor, the entire path up to the root, is also conditionally true. Conditionally false means unconditionally false. It's not the only way. It's just a statement saying, okay, we just should be interpreted as not conditionally true. So it's not even conditionally true. Okay, so at birth, every node has a label saying, a hidden label saying, is it conditionally true or false? So if it's conditionally false, there's no way it's going to be true. Nothing emerging from it is going to be true, but this is hidden. It's not announced, and it will stay hidden till I tell you how it's actually revealed. Okay, and this, there will be some probabilistic process. We will talk about how these labels are generated, and then it will have a public, every node will have a public statement saying is this true or is it false. So Lebesgue's paper in 1904 was proclaimed true. In 1917, let's say it was proclaimed false, because now we realize it's false, and so a proclaimed false paper is definitely false. A proclaimed true paper is possibly true, possibly false. Nobody has said that it is false yet, and all of knowledge today is proclaimed true. Okay, I mean nothing really is unconditionally provable. It's just, yeah, I mean nothing seems to be contradicting it. Okay, so these are the two states. Yeah. Good. If we don't consider the semantics here, so yes, there can also be cases where you have two papers and both of them are contradicting each other. We know that at most one of them will be true. It could be that both of them were false. So proclaimed false is easier to deal with. Yeah, yes. Things which are actually false, we can maybe discover an error and say, look, I don't know whether the theorem is true or not, but this proof has a spelling mistake here, and that's the end of the proof. So falsehoods can be stated. We might never be able to conclude that, oh, these statements are definitely true. You could have correlated events in the tree. We don't model those particularly. We don't really draw links between these two, saying, okay, these two need. Yeah, the joint distributions will evolve everything by a very simple independent process. Yes.
And so this notion, if a node is turned out to be, if it is false, then anything below it's also false. But you might be using partially a theory and not the entire.
Yeah, exactly. So right. So when.
What does the relation?
So for us, the relationship really means that, if a paper has three theorems, we would think of it as three different nodes, maybe. And so if you depend on this theorem but not that one, etc. So in the real DAG model, we should probably consider each statement independently and separately. And if you depend on three of these statements, you'd point to all three, etc. Here, for simplicity, just pretend that everything is a single statement. You either depend on it or you don't, and you can only depend on one. Okay.
So you're also ignoring the case where the proof is wrong but the result is correct.
Yes, we are also ignoring the case where the proof is wrong but the result is right. And that's again for the same thing. If it is to be true, then you would come up with a new proof that would be a new node somewhere else, and then you can all try to link to it again. And so there's definitely lots of things about detailed things. In fact, let me see if that slide comes up here. I'll get to a slide which will also talk about this in a minute. All right. So now we have to. So we've defined what is the structure by which knowledge is being represented. There's hidden truths and falsehoods, and there is proclaimed truths and falsehoods. And now let's talk about how this knowledge process grows. How do we generate a new piece of knowledge? A new piece of knowledge is a new node, has to decide whom to attach to. And we chose the simplest model that we could think of, and the most common one in these kinds of literature, which is the preferential attachment model. So if a node has a lot of citations, a lot of people already pointing to it, it's more likely to be chosen as the next parent of a thing. So when you come in, you look at all the nodes, you eliminate all of those which are proclaimed false. These we will not actually connect to. So these are announced as false, no more citations to Lebesgue. But though I don't know if our paper actually has a citation to Lebesgue now, but no, it's one of those where it doesn't rely on the correctness of Lebesgue. So yeah, we amongst all the proclaimed true nodes, you pick one with probability proportional to its out degree, or probability growing with its out degree. It's really strictly we use 1 plus its out degree. That is to suggest so that a newly born node which has out degree of 0 also has some chance of being selected. Okay, so just to make sure that that happens. Okay, so does this make sense? Any questions about this? Yeah. No, only so with probability proportional to number of proclaimed true children. Great. And the new node is always proclaimed true in this thing. Okay. Now, errors. How do they happen? How does somebody get to be so these conditionally false things are saying these statements are false even if their parent is false, and this is a hidden thing. It's a label associated with the node at birth, and it's just obtained by an independent coin toss. Okay, so it comes up heads with probability epsilon. So epsilon is going to be one of 3 parameters that will associate with this knowledge process. It is the probability of an error. Okay, and so we might produce a tree that looks like this, and now you might say, okay, look, this node has come up, it chose it has chosen its parent, and now we'll decide whether it's going to be true or false, and with some probability we'll toss a coin and then it'll turn out to be conditionally false or conditionally true. And sorry, now coming to this thing, when we were coming up with this model, all of these models are patently inapplicable to, they're not very good models of knowledge. So why are we studying it? I mean, there's an old adage apparently that comes from these probabilistic, probability and statistics, that all models are wrong, but some are useful. So you can still possibly get some good insights by looking at these kinds of processes, and that's up to, and we'll see at the end of this if we are learning anything interesting or not. I think we may be learning something which is not necessarily quantitatively trustworthy, but something that might say, oh, here are some parameters that we might have wanted to pay attention to. Okay, so back to our thing. Now let's talk about, we've talked about how the knowledge grows, we've talked about how errors creep in, and you can see that as this is creeping in, there's an epsilon probability that on any path, any node is actually proclaimed false, and pretty soon if the tree goes on forever at height much larger than 1 over epsilon, every node is going to have some some conditionally false ancestor. So eventually all of knowledge will be false unless we do some checks. So let's see what is a check. A check is going to be a very simple process. What we are going to do is at birth, a node will go up its parents and its parents' parents and parents' parents' parents, and check to see if any of them is what their hidden labels are. Are they conditionally true or conditionally false? When they do the check, the truth will be revealed. Okay, so if you open a node and it says conditionally false, that's the end of the story. Everybody below it becomes false, and everybody below it will be proclaimed false. Okay, now let me try to explain what. So in this example, for instance, here's a new node. It came along, we had chosen some parameter called k equal to 2, and that will say that we will check 2 levels above this node and open up their labels. Is this conditionally true or false? Is this conditionally true or false? It turns out that the top node was conditionally false, so as soon as that happens, all of these nodes will be labeled proclaimed false, and that's the end of that story. Okay.
So why are you assuming that a conditionally false node will eventually become false?
Will eventually become false. Okay, good question. So yeah, why don't I actually answer? So look, every node is going to eventually have infinite degree, I mean arbitrarily high degree, okay, because at each time step there's some positive probability that you will have a child, and the number of children grows with time. So each child that tries to attach to this node will try to open this up and see, is this proclaimed false or not, is it conditionally false or not. But notice that checks are only performed with some probability p. Sorry, this is one parameter I forgot to mention. So every node will decide, should I do a check? If I do a check, I'll do a check for exactly k steps, and this thing, whether I do it or not, is determined with probability p. But once you have like much more than 1 over p children, very likely at least one of them would have opened up your label and they would find out that you're wrong. Okay, does that answer the question? Great.
So if it finds that it is conditionally false one of the parents, so still it will perform this experiment again, or will just attach that with child?
So as soon as this is conditionally false, everybody underneath will be proclaimed false from that point on, and for our purpose it doesn't matter whether a proclaimed false node actually exists or not. because nobody is going to try to attach to them. Okay. However, so suppose for instance somebody tried to attach to this node, so let's say, somebody tries to attach to this node, no, okay, I'm only telling you proclaimed truths or false. Suppose this node is also conditionally false, hasn't been discovered, and somebody tries to attach to it, turns out this is proclaimed false, okay, so I mean conditionally false, so it's probably proclaimed, this will be proclaimed, but look, this guy is still going to be true, and it's going to proclaim true, and it's going to go on, because nobody tells this node that your parent just got discovered as false. Once you're discovered, you have to do a fresh search starting here and find out if it's false. Only the path will be changed. And this is some sort of, okay, couple of choices. Why did we make these choices? One, we wanted to say for every, what's our incentive to do any of this work? We want to actually prove new theorems, we want to discover new units of knowledge, we want to add to this tree. Unfortunately, we also realize we can't just keep adding to this tree willy-nilly, we have to go around checking every once in a while. So we are willing to do some amount of check, and there should be some sort of a constant trade-off between how much time I'm willing to do in checking and how much I'm willing to do in for my own rewards. So we don't want to do an unbounded amount of work. K should be some fixed constant, and P should also be kept under control so that we don't spend too much time doing the checks. If P equal to 1, everybody is checking everything, it's like a lot of overhead. We would like to have a small value of P and as small a value of P as we can get away with.
So one question, when you are trying to attach it to one node and the node is the prospective parent, and you check that if there is some error and you declare that there is some, wouldn't it also make sense to check up in the tree, because if that node has error, then there is a high chance that the parent of that node might also have some problem.
A priori there is no reason why the parent of a false proclaimed false node should also have a thing. So in general, proclaimed falsehoods, I think it can, it looks, the structure really looks like this. There'll be like all kinds of proclaimed false things, but there's no necessary reason why a child of a the parent of a proclaimed false node should be false. Okay.
It means that I am only declaring it the node to be false is the immediate node to whom I would like to attach it to. Otherwise,
we will go through the whole path that we actually explored and go to the topmost node, which was, so there is a length k path that we are willing to explore. If this tree happens to have very large depth, we will only explore k steps of it. In those k steps, we will do the full marking. So the highest node which was false, everybody below it will be declared false, and if none of them were discovered to be false, we will just merrily attach ourselves and proclaim ourselves true.
and that's the trade-off you have with the time when you use them.
Exactly. So if you're willing to go all the way up to the root at each time, maybe things would get better. In fact, it's an interesting question. If we were, can you pay for a very small p by having a very large k? Can you pay for a very small k by having a very large p? These are the kinds of questions that we were trying to explore here.
When you're attaching to a node, it's not necessarily a leaf. It could be anywhere else.
It's anywhere, exactly, yeah. In fact, with preferential attachment, the most likely node in expectation would be the root, etc. Yeah. Okay, and the public space, sorry, I should have gotten to this thing. So as soon as this node was discovered to be conditionally false, we turned everybody proclaimed false in that path. And so that's the summary of the model. Any questions about it? So the three parameters are these epsilon, the p and the k. Epsilon is the probability of an error, p is the probability of a check, k is the depth of a check. We could have done something a little bit more sophisticated, saying k is a random variable which will have certain mean, certain expectation, etc. But we just, we were not able to get very precise models. If we were getting very, very precise answers of the form, this p and this k is good and stable, and this p and this k is bad, etc., etc., we would have probably tried to allow k to be a random variable and p to be a random variable, etc. But for our purpose, just calling it a single constant was good enough because we are only going to get some crude results.
Not marking the siblings as that way kind of corresponding to when a paper is discovered as false. Everyone who cited it, the authors will get a notification that
Right.
this is cited as false. Recheck it.
Yeah, I mean, so that was sort of it's a question. I mean, you could say that look, in an automated universe, that's not a lot of work, and so why not ask everybody to do it? But on the other hand, in an automated universe, we could have just checked everybody also. I mean, you could have just gone through the whole descendant tree and told everybody that you should be false. Somehow it's not happening. I mean, even though these things could be in principle automated, I mean, by the time, I mean, when I've had quite a few errors in my papers, couple of retractions, it takes a long time for that retraction to go out. It's not sitting under that same time pressure as the new paper that I want to publish. So even though these errors should be corrected, and I appreciate it as much as everybody else, I'm not spending in the maximum amount of effort on it. So somehow controlling the
Once you find out that once somebody retracts, then nobody realizes that this paper I used
has been retracted. Yeah, it's not, that's totally true. And on the other hand, which is, yeah, exactly. But on the other hand, I think it just doesn't happen. I mean, you get those emails and you ignore it anyway. I mean, say, oh, it probably doesn't matter to me. So, yeah, this is the model. And we just wanted to keep the amount of work to be an absolute constant for every new node that was generated. Yes, question.
In an effect model, how often you check it? So, but is there a probability of the check succeeding?
Okay, good. So we folded the two things together. You could think of it as I try to do a check and then my check may also be faulty. But then you might just combine the two of them into saying what's the probability that my check is not faulty when it does it. And so that sort of led to this thing. The other thing that we were a little worried about, we didn't want to allow for this thing of a faulty check process in the false negative sense. We don't want a true paper to be declared an error because somebody's not checking errors carefully. So this way that never happens. The only thing that happens is that papers get published and then later they get retracted because there's an actual error.
So this is not communication. Knowledge getting generated. It's not like a Chinese whisperer or something.
It's not communication. It's actually, yeah, each unit of knowledge is a new piece of knowledge. Right, yeah. We have a related...
Sort of more sophisticated error correction if it was just...
Yeah, we do have a paper on the other kind of process. And one big difference there is that there typically you think of the graph as being fixed, but here the graph is growing with time. And knowledge is growing, and so that's, yeah. All right, so the phenomena that we were interested in are, so the simplest phenomenon that you can consider is the following. Some node comes in, conditionally false, okay, and for a while it's producing children because it's proclaimed true. And then after a while, maybe what happens is you go through this thing and it became discovered, and all its children got discovered, all their children's children got discovered, everybody's discovered. Now, if this happened, this is a nice outcome. This is what we would have expected to happen. Once you're conditionally false, everybody below you should be proclaimed false eventually. And if that happens, then we say that the error effects have been completely eliminated, because from now on nobody's going to try to attach to this tree. This tree is more or less non-existent. Some growth happened, but who cares? But so we say that error effect elimination happens if this kind of an event happens with probability 1. For every conditionally false node with probability 1, eventually everybody in its descendant chain is declared to be a thing. Now, we are not asking the question, when does the root disappear? That will definitely happen. With probability 1, the root will eventually be declared proclaimed false, because it's going to keep attaching children. Each child that it tries to attach to it has some probability of discovering it. So at some point, with expectation 1 over p or some such thing, it's definitely, when it has that many children, it's going to be proclaimed false, definitely with probability 1 as time goes to infinity. But we want the whole thing to go down. What else can happen is this guy produces a bunch of children, then dies, and then those guys produce a bunch of children, and then they die, etc., etc. So the next generation is always there and bigger than the previous generation. And you would expect that this is a kind of a branching process where either the next generation will be a little bit bigger than the previous one or a little bit smaller, and if it's a little bit smaller, you will all live, or if not, you will die. When does this happen? Does this happen? For what choices of P and K can we say that error effects get completely eliminated, and for what choices of P and K the error effects survive? Error effects survive if the probability of this kind of a death is strictly less than 1. Okay, bounded away from 1. So you do expect that with positive probability, as soon as this node is born, the first child that tries to attach to it discovers an error, it's all over. So just saying that with positive probability this kind of a situation happens is not good. We really want it to happen with probability 1.
Also, complete elimination is not very helpful when it took a long time to...
It's a good question. So see, so the complete elimination by definition happens in a constant amount of time, in constant expected time, right? I mean, either it happened in some time. How much time? Well, some function of epsilon p and k, but it's some constant based on those. It's not a function of the time at which you are. Also, time should be measured in these cases relative to the number of children you produce, because if you're not producing any children, you're not going to make any changes over here. Suppose this is one conditionally false node in some huge network. Almost everybody that's coming in is trying to join elsewhere, and nothing's happening here, so this is not discovered. But is that bad? Well, no, nobody's reading this paper. It's going to be fine if it's wrong. So we measure more or less time as the number of descendants in this tree, and you ask the question, how many descendants? Well, it's going to be some constant. Great. So these are the questions that we wanted to ask. Let me just make sure.
But the checking actually begins because of the new node that you are trying to attach, right? And that depends, like wherever you are trying to attach, there you are doing the checking. It's not, doesn't depend necessarily the depth.
Yeah, it's not the depth. So exactly. So okay, if you're a node that has produced lots of children, which have lots of children, and you have a small value of k, and you attach at the leaf level in this new tree, which happens with significant probability, constant probability, you're going to try to attach to a leaf of a tree. You will. It turns out that you might not even check the root at this stage from now on, right? So once you get enough depth, you might sort of never discover the root is wrong. But of course, you don't always try to attach to the leaves. You're also trying to attach to other nodes, etc. And with some probability, you're even trying to attach to the root itself.
What I mean to say is that some nodes which were inactive can suddenly become active, right? So do you also have probability that what is the probability that a node might get affected?
The probability with which a node gets active is just proportional to its degree, right? I mean, the only thing that changes, only reason people try to attach to you is because of the number of children that you have. So in some senses, it's already built into the thing. Okay. All right. So, so by the way, when should I stop? 3:15. Okay, sounds good. Sorry. No, okay, sounds good. I'll try to wrap up a little before and hopefully take questions, but if you need to run, then just let me know and I'll wrap up in a minute. So beyond this error effect surviving and eliminating, what are some other questions that you could ask? You could ask some quantitative questions. So suppose error effects are surviving. Actually, it's not that processes even die. They even keep producing. Still, I start with a conditionally false node, I start with a conditionally true node, and now let these two trees evolve. Are they going to grow at the same size? So imagine that I started off, my whole structure of the universe was some node at the top which is conditionally true, one child conditionally false, and let's say now let's just let this process evolve. Are you going to see, of course you're going to see a conditionally true node should grow a little bit faster. Why? Because there is always some probability that you will discover errors over here, and then this node dies. The probability of death is in general higher over here in the initial stages, and that should have a long-term effect of a constant factor. But could it be that this is actually growing by a sublinear size, whereas this root has grown to a node of size n after some number of steps? This one might be n to the 1 minus epsilon. Okay, could that be the kind of behavior? So how large are the component sizes? This is a kind of question that we would like to understand. We don't have great understanding here, but we have some careful cases. I won't even bother to state the results here. Another question that we asked is what happens on the other side? Error effects are completely eliminated. Okay, but still, you might ask the question, okay, every node sort of sticks around for 100 units of time. This comes back to your question of this constant factor. Every node sticks around till they have about 100 descendants, and then they die. Okay, and everybody in that whole tree dies. But every conditionally false node gets to have an expected 100 things. That's a lot of falsehoods sticking around. And I mean, epsilon probability is the probability of an error, but what you're seeing when you look at the whole tree is 100 epsilon kind of behavior maybe. Okay, so can we say something about this is a setting under which if you control for errors carefully, etc., then of course at any moment of time epsilon fraction of the things are probably going to be wrong because they were the latest generation. They never had a chance to even get a check done on them. But can we just say that epsilon plus little o of epsilon is the total fraction of errors in the tree? Okay, if we do checks carefully, can we get it down to something which is very manageable? We do talk about these kinds of results in the paper, and I'll sort of just point you to those statements. For the statements, I won't state them very precisely here. Okay, all right. So now turning to some results. Most of our results are in the just looking at this question of I started with a single node which is conditionally false. How long before everything is eliminated? And one thing that we did in the paper was to actually look at this thing in this following very extreme case: epsilon equals 0. Okay, you start with a conditionally false node. How did it happen? We just allow this one thing to happen. It's a singularity. From now on, there are no further errors. Children are produced, children are produced, children are produced. They are all conditionally true, but of course everything is false because the root is false. So how long before this entire process is completely eliminated, or does it actually go on to infinite size with positive probability? Okay, so this is the question that we wanted to ask. And the funny thing is, okay, so the result over here says if k equal to 2, then for any p, even p equal to 1, even more, every p less than 1. Okay, yeah, I do need the strictly less than 1, but really as close to 1 as you want, the error effects actually survive with positive probability. Okay, so what does k equal to 2 mean? Let me explain what k equal to 1 means. K equal to 1 means I'll check my parent, and if they are proclaimed false, I'll declare them, if they are conditionally false, I'll declare them false. And this will happen with probability p. This is terrible because once I'm born as a child of a conditionally true child of a conditionally false parent, nobody ever checks me anymore, because the only people who will come to check me are my children, and they will check me and I'll be conditionally true, I'll be true. Nobody goes to my parent, realizes they're wrong, and percolates the result downwards, right? We need some percolation, that a proclaimed true node can be proclaimed false later. If k equal to 1, that can never happen. So k equal to 1 is not interesting to analyze. K equal to 2 is the minimum interesting parameter. You check your parent and your grandparent, and this way if your parent is proclaimed true but your grandparent is false, then you can actually percolate this thing downwards. Even with this case, k equal to 2, you can check with probability arbitrarily close to 1, this is going to be not good enough. This process actually goes on to live forever. How did we prove this? Somehow a bad configuration is like the following. You have a node with a some space here. Okay, great. And there's the thing. In fact, that's the perfect kind of space, because the bad configuration is something that looks like this. Okay, so there is a root which is false, proclaimed false. This is a proclaimed true node, and we are looking at this. Till everybody here is conditionally true. Okay, everybody in this tree is conditionally true. We are looking at epsilon equal to 0. Till somebody comes and tries to attach to this node, they will not really discover an error. Okay, so the probability that they will come and try to attach to, on the other hand, if they don't attach to this node, they preserve the structure. It's just a bigger n here. Okay, so how long will it be before this one node is eliminated? It turns out to be some sort of a harmonic thing. So if you have n children, the probability that you'll kill this is 1 over n. And if you have n plus 1 children, otherwise you have n plus 1 children, and the probability that you're going to die is 1 over n plus 1, etc., etc. So now this has got an infinite time before this dies. By the time this dies, you would have probably produced a whole bunch of these kinds of configurations inside this tree, right? I mean, in expectation, there should be lots and lots of nodes which have only one child. And so you have created infinitely many of these even in expectation. So clearly, as a branching process, this is just exploding. So that's roughly what happens in this theorem. It basically says you cannot just trade off p versus k in one direction. You cannot just use this is really actually with p equal to 1 that we are doing over here. I mean, if you ever try to connect to this node, we will kill it for you with probability 1. But there's just a huge probability that you will not connect to that node, and it just keeps growing up over time. I'm sorry? The very first time when the node is born underneath, you need p less than 1. Other than that, exactly, yeah, good.
So does this happen for any k, because all you need is k length chains which are conditionally true, and then you're got to be there?
Excellent question. So here is the second theorem. So for every k greater than or equal to 4, there is actually good news and bad news. Okay, the bad news is even you can't just use a very, very large value of k and use a tiny value of p. That won't work. You have to use p which is at least 1/4 in order to kill things. Okay, sorry.
What's the specialty over 3?
What about 3? We don't know. That's the open question in this thing. So we couldn't analyze it. And by the way, we are doing very simple potential functions throughout this paper. So it's like, if you want to prove something grows, we will say, oh, here's a potential function, count the number of leaves, count the number of univalent nodes, etc., etc. When it want to prove that something dies, we'll say, oh, do this exponential potential function on paths, and that will be shrinking at each time in expectation. That's good enough to prove that the process will eventually die out. Okay, so and for k equal to 3, we couldn't find anything. We actually don't know what the truth is, and it's like many of these cases where you say, well, this proof almost seems. I mean, in this proof, we proved that by the time this guy dies, it has infinitely many univalent children underneath. I didn't need to prove infinitely many. I needed to prove 1 plus epsilon in expectation. Couldn't this gap give me some room to work with a slightly larger k? No, apparently k equal to 4 already it really dies, and k equal to 3 probably we just haven't found the analysis which shows that it dies. So there is a sharp threshold, but that's a triviality, because either for every choice of p, epsilon p and k, either the process is going to allow error effects to survive, or they'll be completely eliminated. That's just definitional. And the interesting thing is that this p naught is strictly bounded away from 1. So if you're slightly even, you don't have to check with probability 1, but as long as your probability is sufficiently high and close to 1, you will be able to eliminate error effects completely, as long as k is at least 4. Okay. And yeah.
Is there some places where k and
yeah, so it's kind of a funny relationship. So in fact, I can say something. Yeah, so what really happens is this p times k, the product, is really what is important, as long as you don't mind a whole bunch of small, disconnected, shallow falsehoods. But these things can, I mean, sort of like this, I don't know if you've seen these pictures of the Game of Life screensaver where you sort of shoot something and then there is a layer that keeps growing outwards and then goes on forever. That kind of a process can happen here. You start off, this guy is true, produces a few children and then dies, and produces a few children, then they die, produce a few children and then they die. You are not getting a deep, narrow thing ever, as long as epsilon times k, p times k is sufficiently large. But then to say all these small pieces will also all die out, you actually need p to be sufficiently large, and then it needs to be at least 1/4.
So actually here in that, like, so for instance a paper that is written 100 years ago might be still very relevant, but it, like a large number of them is less relevant and many of the descendants are not relevant. So this time window is actually an effective parameter, right? That when a node is attached, it has its impact for some period of time, and then after that it's...
Good, I see. Okay, so you're asking the question, is this preferential attachment really a good growth model, in the sense that, so my sense is, okay, firstly, I mean, we're working with this tree restriction, which is much more restrictive than anything else. But if we really were right, so Karp's paper on NP completeness should probably be cited in every paper that we write that ever mentions NP completeness, right? But we don't do it. So I think the reason we don't cite old papers is not because legally we are not obliged to cite. It's because, I mean, Karp is not going to come and complain to us. And well, if you miss out somebody else's paper who wrote a paper 2 years back, that's really, and also we are trying to say, okay, what's the novelty of the idea and the things that we are citing. But really, I mean, I think every one of us should be citing, I don't know, Leibniz and Newton and whatever for calculus, etc. So, yeah.
So when you say this survives a positive probability for P less than P naught, like, so what probability will survive? Like 1 over poly K?
No, okay, so, the dependence on K you're asking, that's an interesting question. Actually, I don't think we even have the ability to understand it. All we can say is, all we are able to say is that this expected size of this process is going to infinity, and so it survives with positive probability.
So I want to understand this threshold phenomena better, like completely eliminated and survives with positive probability. So, I mean,
This is just this is a negation of that. That's all. There's no in between ground. So, sorry. Yeah. I mean, it's not like there are many interesting statements that could be made about this, but this is not the part. The only interesting part of this theorem is here, which just says that the threshold is not 1 and the threshold is not 0. Even with positive probability of checking, the process can go off, and for very large values of k, it can go off. And similarly, we don't need to have checking probability 1 to kill the process. It can be bounded away from 1.
So if P depended on the degree, then we would actually have something quite dramatic. Right?
If P,
Yeah, I mean, so you don't check if there are enough citations.
If there are enough citations, yeah, then I agree. Yeah, then we would probably start seeing very interesting things. But then you would also have to come up with a good justification for the function P, and then but I agree that there's sort of lots of rooms for maneuver here. So we were able to find some other parameters which said, when is it that some of the false components are actually sublinear in size? When is it that if false components are completely eliminated, then what is the setting under which the fraction of errors that you see is just the latest born errors, and nothing more than that, not much more than that. And we have some parameters for which all of these hold. In this paper, I think we started asking these questions. We really thought many of these answers we'd just find overnight and then move on to the more interesting ones. We were barely able to even cover the very, very, very preliminary thoughts with some theorems. And I feel that there's just a huge amount of questions that are sort of ripe for opening. I mean, I really think that this separation of error effect surviving versus completely eliminating should mean a lot more quantitatively for what is the size of the thing. So as soon as it turns out the error effects survive, maybe there is a linear sized fraction of bad things which is in addition to whatever is the latest generation. Or maybe as soon as it's completely eliminated, everything else is going away, and one way to control for it is if you look at the number of nodes which have at least t children, that's like a very good, those are almost guaranteed to be true as t goes to infinity, etc. So there could be a lot more that we could say over here, but that we are not able to say here. So I think there's lots of very interesting questions to be analyzed further. I was supposed to do some proofs, but I'm not going to do that. Instead, let me just mention, the mysterious case of k equal to 3, we don't know what's going on. We don't really understand this p naught, what it looks like. All we know is that it exists, and it exists because it's a triviality. At some point, error effects, p is large enough that error effects are eliminated, and so it exists. But what should it be is a very interesting question to understand. And then, of course, there could be, can you obtain similar results for DAGs? I don't know what the motivation might be, but the probabilistic process is very simple and clean. You could just say, pick 3 random parents with probability as in the preferential attachment world, and now tell me what happens. Like with many of these processes, you say, oh look, trees must be almost as interesting to study as DAGs, and then you realize, oh, actually it's much harder to study DAGs than trees. So that's happening to us now. But I think the more interesting question over here is really, if you want to allow co-citations, what would be the right model for co-citations? So now, I think this is a very interesting modeling question that's worth asking. How do you sort of, people have looked at these kinds of things in the ML literature, like topic modeling and so on. If a paper is about a few topics, what kinds of other papers might you cite? So one could study that. Okay. All right. Thank you very much.